Okay, so today we're talking about Chapter 15, which is precast concrete framing elements. So last week we talked about site cast, right? Build the formwork, pour the concrete on site, wait for it to cure, take the formwork down, put some shores up, wait for it to cure a little longer, and then continue building, right? In precast concrete framing systems, we're going to do all of this concrete work off-site, right? And then we're going to put this stuff on a truck and bring it to the site and assemble the building, right? So this is going to be more of a prefabricated way of thinking about building and building rather than something that's built on site as we go. Okay, so a lot of these components are a little bit more generic, and they're used and repeated over and over again, right? So the most standardized precast common element is a slab, okay? Which, remember, we all talked about a slab on grade, right? Similar concept, right? Except this is something that's going to be reused several times in a building. It's typically going to be supported by bearing walls. Those can be precast concrete. They could be some kind of masonry, so concrete masonry units. They could be brick, right, depending on what it is that how you're building the building, or they could be steel, right? So we could have a steel wall with these on top of the steel wall. So they can end up being sort of a hybrid system. We're not going to talk about steel at all today because we haven't talked about steel yet, right? But you'll see that when we get to steel, right? So oftentimes these things end up being mixed, right? So if we look at our basic slab types, we have our solid flat slab, right? Solid concrete profile, right? Kind of your typical slab, right? It's like you would build in a building, except it's done off-site and brought to the site. But it's just a solid piece of concrete with its reinforcing in it, right? We'll talk all about reinforcing in a second, right? The next type is a hollow core slab, right? And you should, if you look at something like this, you should start to say, wait a minute, this looks very similar to the types of things we started to do to site cast concrete, where we removed non-working concrete, right? We pulled some of that out. So we talked about the one-way joist systems and that sort of thing, right? This is basically what we're doing, except it's cast off-site. We get to the double T, right, which in profile looks like two T's. Hence, no surprise, it's called a double T. And then we end up with a single T, right, at the end. And these are working up in terms of their spanning capacities and their load-bearing capacity, right? So we're starting at the bottom and we're working our way up. Okay? So if we start with that first one, this solid precast slab, right, we're talking about very short spans. 1/40th of the span would be the depth, right? And the depth is going to be 3.5 to 8 inches, right? So if we quickly do some math, we're looking at somewhere in the neighborhood of 20 feet in span, if I'm doing that correct, something like that, right? So not too long of a span, but kind of a decent level of span. This is an example of one of those precast concrete slabs, right, being lowered into place over two bearing walls. Okay? Obviously, there's a bunch of reinforcing stuff going on here, and we'll talk about what all that does in a little bit. But the idea is that this piece is cast off-site, brought to the site, and placed where it needs to go. Right? From solid slabs, we move into hollow core slabs. Okay? And these are characteristic by these, right, repeated circle or long oval patterns, right, that are taking out some of that non-working concrete. Right? We're decreasing the weight of the piece, and by decreasing the weight of the piece, we're able to span a little bit further. Right? So they contain internal longitudinal voids that replace the non-working concrete. An 8-inch hollow core slab can span 25 feet. Right? So we're starting to get further distances. A 12-inch slab can span 40 feet. Right? So we got much further distance out of the depth. Make sense? Okay? They're designed for the kind of intermediate span category. So here's an example of a longer one, right? This being not the circular pieces, but more of an oval, right? A longer void in the center. Where's my? I had a stick the other day. Hold on. Right, so if we look at something like this, we talked about before, right, site cast concrete elements. In this example, there's the column, right? We see the formwork as it's slid up. There would be the line of the cold joint as it works up. I know the picture is a little bit blurry. This is a stadium, right? So if you think about a stadium, you don't think about, are these elements precast, right, or cast on site. This would take an incredible amount of formwork to support the underside of that stadium. But if we're building these precast elements, because they're consistent and we can reuse them over and over again, it's a pretty efficient way of building each one of those tiers as we go up, right? So depending on how and what type of building we're going to make, right, these can be more or less advantageous, right? So example of a hollow core slab. This one is not a particularly well-made one by any means, but it is an example of one. You can see that it has some reinforcing in it, and we'll talk about kind of how that's made and the whole process as we go along. But it's helpful to get a general understanding of these, right? Another example here, right? These being a little bit larger, in depth, but instead of being the circles, right, we're taking out more slender pieces. It depends. Different machinery makes it slightly differently. Also, you can see in this particular example, we have this depth here is different than this depth here, right? So they're casting two different types of slabs at the same time, right? And here we are getting one of these slabs into position, right? Parallel lines of support. Here's our support on one side. Here's our support on the other side. And these slabs are being lowered into or craned into position. Okay. Another example here. This is where I was talking about these can rest on steel, right? This is a steel beam. We'll talk about steel in 3-4 weeks from now, right? But the precast concrete elements are resting on the steel. Steel's just providing the support, right? Craning it into position, yet again. One of the big challenges with this is getting it to the site and then getting it into position on the site, right? So before we could pump the liquid concrete into position, now we have to get the rigid piece into position, right? And so you have to have space above for the crane, that kind of thing, right? Another example there. So we move up, right, in spanning capability, right? We get to the double T slabs. This is elimination of even more of the non-working concrete. 1/28 of the span is the depth, right? So we're getting, it's a lot deeper, which could be problematic depending on how much headroom we have, right? And they're typically going to range somewhere between 12 and 32 inches in depth, right? So much deeper. We're not getting into the small ones. This is big stuff, right? Typically the span is going to be 28 feet to 75 feet, right? So we're getting much, much longer spans, okay? We get finally to the single T slabs. It's the elimination of yet even more non-working concrete. A 36-inch deep single T can span 85 feet. A 48-inch can span 105 feet, right? So these are pretty long-spanning elements, right, that can be prefabricated off-site. Now, okay, let's take the 105-foot example, okay? If I fabricate this off-site, I have a 105-foot long thing that has to get from wherever I made it to wherever I'm going to use it, right? Which is not something you could just drive down the. Anybody know how long a regular semi-truck would be? Regular? Yes, 60 feet, something like that, right? So this is like 2 semi-trucks trying to tow it down the freeway, right? You're allowed to do 110, right? But you've got to have the wide load people and the front and the back, pilot cars and all that kind of stuff. So think about the challenges of getting something like that to the site, right? So yeah, it's really great that you can get the spanning distance, but you also have to weigh in how do you get it to the site, right? And so that's the disadvantage that's important to talk about, okay? So all of the precast concrete slabs are manufactured with a rough top surface, right? So this isn't finished the same way we would finish a slab that we stand on here, right? It's finished intentionally rough, right? After it's assembled, so after we put all the pieces together next to one another, right, we pour a topping layer over them, right, a layer that's on site that ties them all together, right, which is really important because it's providing that structural continuity between pieces, okay? That also gives us the opportunity to put a nice finished surface on the concrete, right? So we leave it rough so it's scratched so that the concrete topping will adhere to it, right, and then we finish the surface on site. Yes, sir? Make sense? Okay. So, right, you may be saying, wait a minute, I thought these were fabricated off-site, right? Well, isn't this making it on-site, right? The difference, though, is that these elements are structural pieces, right, that are staying with the building. So you're not building the formwork first, right? You're casting on something that's staying with the building. So they're providing structural strength. The topping just ties them together, right? The topping's usually going to be about 2 inches thick, right? And once it's cured, it becomes part of the overall building structure, right? So if we're looking at a close-up of a hollow core slab, something like this, this is the joint between two hollow core slabs. Obviously, this is very close up. We don't even see the hollow core pieces of it, right? They would be over here and over there, okay? At the edge, in this particular example, right, we have this notch that's been left out, and we have this series of rebar pieces, right? This one coming from here, right? There's another one from this side, but then we have an opposite interlocking piece coming from this piece, right? We will then pour the topping on top of this, and it will fill this cavity between the two, right, and lock the two pieces of rebar together, making it one solid slab, ultimately. Does that make sense? Right? So that's how we tie these things together. Right? Another example here, we're looking down, right, on this particular example. You see that we still have those little gaps here, not as big as that last one, not as much rebar. Depends on the structure, right? We also have regions, right, where solid concrete is going to be poured once we pour the topping, right? This is going to help tie above wherever our beams are together, right? So we're spanning from here to here. This will end up being solid concrete. Sorry. You get the idea. Okay? So reinforcing can sometimes be used in the topping itself, right, to help tie that and add additional structural value together. You can also use regular concrete or structural lightweight concrete, right, either in the slabs or in the topping, depending on what the engineer specifies, right? So you have some more control over that kind of stuff, okay? So what else do we have? We started with slabs, which are, again, the most common element, right? But we can precast a lot of other things, too. So if we talk about beams, girders, and columns, they're made in several standard sizes and shapes, right? And so these are going to be consistently reused over and over again. If you're wandering around and you're starting to pay attention to these sorts of things, you will see these frequently. Okay? So we have our regular old rectangular beam, right, which looks like a rectangle, has reinforcing in it. Again, we'll talk reinforcing in greater depth as we go along. Notice that we do have all of these little loops that come up out of the top of the beam. What would those be used for? Lifting them into place. What else? The topping, it's going to help tie the whole thing together, right? So we're planning ahead for that sort of thing. Okay, we have an L-shaped beam, which is good, right? It has a nice little ledge on us that would allow us to support a slab or something, which we'll talk about in a second. We have an inverted T, right? Same kind of thing here, right? And then we have this AASHTO beam, which is the American Association of Highway something, whatever, right? State Highway, thank you, right? State Highway, whatever. It was originally developed for the highway system, but we're starting to use them in buildings, which is why they're there, right? I probably have a slide in like 3 or 4 slides that'll say whatever it says, right? So this is our rectangular solid beam, right? Kind of the simplest piece to understand. It looks just like a beam that we would normally have, except it's cast off-site, right? Examples of rectangular beams, right? This is what we were talking about here with those pieces that are going to tie the topping layer in. This is the little loop that helps you pick it up and move it on a particular site. These are the reinforcing that are put in, right, ahead of time. We'll talk about that reinforcing in a little bit. So they're pre-tensioning pieces. This is the inverted T, right? This is a T-beam that's not inverted. We know it's not inverted because we have all that topping or all the rebar sticking out the top, right? So shapes can vary depending on what particular type of building you're going to use. You're going to pick a different type of beam, etc. So ledgers, right? These projecting ledgers, right, are these little shelves on the L-shaped beam, right, and the inverted T-beam, right, are great because they can help us conserve headroom, right, in the overall height of a building. If I had a beam, let me draw this for a second. Right? If I had a regular beam, right, rectangular beam like this, and I needed to put a precast concrete slab on top, right, I put my precast concrete slab on top. Let's put another one going this way, right? There's a little joint in between them, something like that, right? Then I pour my topping on top of that, and then I have my floor, right? So if I'm standing down here, right, this is quite a distance. Make sense? But if I use something like this, like an L-shaped beam, for example, right, I could take this slab and move it down, right? Well, we'll say it's going right here, right, which lowers my overall height between floors down to there, right? And now I can put my little topping layer on top of that, and this got much shorter, right? So I'm conserving headroom. That's what I mean by conserving headroom, right? By placing the slabs down on the ledgers instead of up at the top. So here we go. Here's the American Association of State Highway and Transportation Officials. Right? This was originally designed for efficiency in bridges and highway overcrossings, that kind of thing. If you drive on the highway and you look up, not hopefully while you're driving, right? When you go under one of these, there is a very high likelihood that you will see these. Right? They're extremely common. They're great precast elements. They're very efficient structurally, and they're used all the time. Right? Now some of them are used in buildings, depending on the spans that you need and the relative availability of them. Again, it all depends on what prefabricator plant you have and whether they have the capability to make those particular beams. Right? So precast wall panels. Right? So we started with slabs being the most common. We moved into beams and girders, right? And we'll end with wall panels. They can be pre-stressed or conventionally reinforced, right? They're used as load-bearing wall sections, okay? Not particularly common around here, but they do exist, okay? Typically, they're going to be 3.5 inches to 10 inches thick. They're going to span 1 or 2 stories in height, right? And if they're pre-stressed, the tendons are going to go right through the middle, right, to provide not an off-center. You don't want a camber. You don't want a bow, right? They're going to be straightest if they're right in the center, and that'll protect them against buckling. Notice down here, right, not only do you have wall sections, but you can have precast stair sections, right, which can be really useful. Why they had to label them stair, I don't really know, because it's pretty obvious that they'd be stairs, but you can go figure it, right? Okay. We can move from the solid wall panels into the hollow core wall panels, right? Same technology as we talked about between the standard slabs, right, and the hollow core slabs. This time we're just in wall panels. We have a standard wall panel and a hollow core wall panel, 12 to 14 inches in depth. They can contain some kind of integral styrofoam to increase the insulation value of that particular building. Usually it's some kind of a proprietary system for how they mix it in. Right? It can span up to 4 stories in height, right? So you can get a little bit more height out of it. Right? You can move from there into T-wall panels. So you can kind of see a similarity, right? These are all things that we talked about as slabs being this kind of span, horizontal span. We're using the same elements now in vertical, right? So anybody seen a building that looks like this? Fry's Electronics is the best close example of this, right? So you can all go to Fry's Electronics and you can see this sort of thing, right? Even greater depth and height, right, because we've got the T-wall panels. They can be single Ts, they can be double Ts. It just depends a little bit. Now, if we look at a building like this that's built out of these prefabricated elements, you notice something that's kind of missing? Windows, right? So if we're thinking about these precast elements as wall panels, right, they're really efficient if we have a building that doesn't need windows, right, and doesn't need openings, right, and we could just shell it in, okay? So in this particular example, this door is relatively easy because it's in between 2, right? This took a lot of effort to figure out how to make that door and make it fit, right? Up above here, no windows, no openings, really efficient, really economical, right? But if we wanted that to be full of windows, this system wouldn't be that economical, nor would it be as structurally sound. Okay? So another example here, right? And if you look very carefully, you can tell this is a double T. Right, there's a line there and a line there for where they seam together. And in this particular example, we have some windows cut in the front building, not in the back building, right? And notice that the windows fall very symmetrically exactly in the center of one of these panels, right? And so it makes it a little bit easier. Could we have a window that spans one of these T's? That would defeat the purpose, right? So you're very limited in what you can do in terms of what kind of apertures can go through that particular wall. So there are a bunch of proprietary wall panels that are for residential construction. I don't have a lot of personal experience with these kinds of proprietary systems, but if you're interested, just Google it, and there'll be a bunch of systems that are out there. Okay? So if we start to look at how these things come together as a whole, right? In this particular example, it's parking garage, which is a very common use of this kind of a structural system, right? We have our double T slabs up top here, right? Those double T slabs are being supported by a frame of columns and girders, right? There's your column, right? There's our prefabricated girder, right, with its little L-shaped, right, beam with the ledge there. That ledger accepts these double T pieces. They rest on that. That's how we transfer the structural load, right? Another example here, kind of in a more residential setting, hollow core slab supported on a concrete load-bearing wall, right? Here are our concrete load-bearing walls. These could be cast on site. They could be prefabricated, depending, right? And we have our hollow core slabs here that are making the individual floors. Okay? Sometimes it's just helpful to see them all put together. Another example here, right, where we have a precast wall panel, right, with a nice little built-in ledger. That then supports the double T, right? We have our beams and our columns in the center. The double inverted T with the ledgers there support the double T slabs, right? Transfer the load that way. Okay. So if we move on to the manufacture of precast elements, let's get to the actual fabrication plant and talk about how they're made. So if we need to make one of these elements, right, we need to have some place to make them, okay? And it wouldn't make sense for a prefabricator to, say, build the formwork out of wood every time they were going to make one of these, right? It'd be too much work and waste too much material. So they need some kind of a permanent form that they can reuse over and over again, okay? And so this permanent form is called a casting bed, right? Because it's permanent, it's existing. It's something that's reused over and over again, right? The casting bed is going to average somewhere between 400 and 800 feet in length, right? So this is really long, right? And if we think about it, it kind of makes some sense to be able to, instead of just casting one little piece at, say, 60 feet, right? If we can cast 10 of them and it equals out to be 600 feet, right? In one bed, it makes it more efficient. We can make 6 of them at the same time, right? So generally, these are on big open sites where we can have these very long casting beds and a that's a piece that ended up on the Bay Bridge, right? That was when I was on site when they were casting those pieces, right? So how do they do this? Okay, what they do is at the ends, right, of the casting beds, right? They have these nice solid blocks, and I'll show you pictures so that makes sense. These nice steel blocks that are called abutments, and they string these tension cables in between the abutments wherever they belong, right, inside the beam. And then they stretch those cables, right? And they add in these what are called transverse bulkhead separators, right, to break that big, long 600 feet into its component 60-foot parts, right? So if we look at it here, this is the casting bed. It gives you some idea of the scale. This guy is standing inside it. The two sides of the casting bed, right, have been hydraulically moved apart so they can more easily access and add the reinforcing in as necessary. You could see the cages of reinforcing, right, that have been put in already here, right, and a couple guys working on it. But you can also see how far back this goes, right? Likewise, you can see the people up top looking down inside that particular formwork. The formwork's made out of steel so that it can be reused over and over again and has a nice finish to it, right? Looking again at it, this is that abutment that I was talking about on one end. It's a big steel piece. You got the little soda can here to give you some scale, right, which is always good, right? And so this abutment is where we're going to string all our cables, right? And so you can tell that this particular region is where they put the bulk of the cables, right? It's nice and marked out so that they can figure out where they go. And they're going to string the cables from this end all the way down through that casting bed to the abutment on the other side, right, so that the cables run all the way through this particular piece. Right? So there it is, stepping back a little bit. And you can see, again, because of the size of the formwork, we have a lot of flexibility in terms of how big of a particular beam we can cast. Right? How tall this beam is, and therefore how far it can span. You can see the set of these, right, reinforcing pieces that are ultimately going to be put in just in queue waiting, right? Hard to see, but right here is a spool of the steel cables that they'll use, right, the tendons. There it is, right, a little bit better. There's our steel tendons, right? Those are going to run through those little holes on the abutment all the way to the end of the other side, okay? So after we stretch those tendons, right, they'll put in any additional reinforcing, any extra weld plates or anything that needs to be embedded in the concrete, right, any extra things that are specific for this particular beam, they'll put those into place, right? Then they'll pour the concrete into the bed and they'll vibrate it to eliminate any of the air that's around it, right? If slabs are to be used without topping, they're finished right then. Right? Most of the time they're used with topping, so they're left rough on the particular surface. Right? So if we look down inside, right, we're putting our reinforcing into place. We don't have those tendons strung yet. Right? Easier to put these in first. Notice we do have the chairs, keeping these nice and consistent. Right? Okay? After we poured the concrete, live steam or radiant heat is applied to the formwork. Right? That speeds up the curing process so that in 10 to 12 hours, the concrete reached the majority of its strength. Right? So we're vastly accelerating the cure time of the particular concrete. The nice thing is the next morning, right, not only have we steam cured the concrete itself, but we've also steam cured all those test cylinders that I talked about, always pouring to make sure that the concrete from the batch plant turned out correct. Right? Right there on the site, they can test those test cylinders, make sure all the concrete lived up to its desired strength. Before this beam even leaves the plant, they know it's the correct strength. Right? So it's very efficient. Right? If something was wrong with it, it's easy. It's never been installed in a building. You just toss it. Well, it's not that easy. It's 800 feet long, but you get the idea. You just toss it. Right? When it's not the right strength, then it will need to be thrown out, so to speak. And by throwing it out, basically they'll cut it up into pieces, take it to a plant that will grind it up, and they'll use it as aggregate in something else. Right? Most of the roads we drive on and stuff have a certain amount of base rock underneath, providing the support for the road. Most of that is ground up stuff that we've demolished and reused. That's the most common base. Okay, so after, right, we've reached the next morning. We're ready to pull this out of the forms, right? What we do is we cut the tendons. Okay, so remember the tendon was put into the formwork, was stretched. The concrete goes around it and cures all the way around it, right? But the tendon has no covering on it. It's just the raw steel against the concrete. Okay, so the concrete actually bonds to the steel, right? Just like it would in a traditional building, right? It bonds to that steel. So when we relieve the tension in these pieces, and we do this by just cutting through the tendons, right? When we relieve that tension, right, the friction of the bond between the concrete and the steel, right, the tendon shrinks just a little bit, right, because that tension is released. And when that happens, right, we immediately get that intentional camber, right? That little bit of bend, if it was intentional. If it's meant to be perfectly flat and the tendons are all right in the middle, then it won't camber at all, right? But the whole beam will go into compression. If, like the beam we saw, right, where all the tendons were in the bottom, right, as soon as that's released, the bottom will go into more compression, and that'll develop an artificial arch to that particular beam, right? So it's an immediate sort of thing. Let's see if we can move on, right? So here we are on site, right, with the final beams, right? Notice the bulk of the reinforcing's at the bottom. There is some at the top, but the bulk of it's at the bottom, right? Those are all hanging out, so we know that they've been cut, right, and they're all pre-tensioned pieces. All those wraps, those ties, they're using what would be like a giant slinky, right? They string that in, right, and then they pull this down from one end to the other, and they just tie it off in a few places, and that provides that other layer of reinforcing. Make sense? Right? So in this particular example, here's one casting bed. This is obviously much smaller in scale than the one I just showed you. Another casting bed, right? And these are both for piles or columns. Right, so they'll do those two at the same time. Okay, so the manufacture of hollow core slabs is slightly different than these other precast elements. There's three different methods for how it's done. It depends entirely on what the prefabricator equipment is, right, and how they go about building it. Right, so it's going to vary a little bit by plant. Okay, we have the extruded process, we have the wet cast process, and we have the slip form process. Okay, and there's advantages to each. So the extruded process, right, basically takes this extrusion device, right, which is like a hopper, right, that you dump the concrete in. It's a very stiff, dry concrete mix, right. That is pushed through a die, right, that represents the ultimate shape that you want. It's kind of like frosting a cake, if you've ever done that, right, where you put the frosting inside the bag, and you have a tip that has whatever cross-section you want it to be on, and you squeeze it through. Right, that's what's happening here. We're squeezing the very dry concrete into the shape we want based on the die that we have on one end of the machine. Right, vertical openings, weld plates cannot easily be cast into this. Right, because the machine has to push the concrete into its form, and then it keeps backing up and keeps pushing more in. Right, but it's hard to say, well, wait a minute, I want a little opening here, or I want a little steel weld plate here. Right, it's just one process, start to finish, right? So there's not going to be a lot of openings. There's not going to be a lot of special modifications that are going to be done, okay? The wet cast process is slightly different, okay? In this example, we have a long bed, right, that we're going to cast into, and we pour a small thin layer in the bottom of the bed, right? After that, we put a second layer of concrete on, but we put these collapsible tubes or some kind of sand aggregate that we can get rid of, styrofoam maybe, right? And we create those voids artificially, right, on top of this surface, and then we pour the concrete around those voids, right? After we've done that, right, we put a topping layer on, right, on top of those voids, right? And then we deflate the tubes or we pull out the aggregates, and we end up with the voids. Right? So it's not as precise, it's not as clean looking, right? But in this particular example, it's very easy to say, you know, I want a void in here, I want a window here, or I want an extra weld plate here, or I need to attach this to that piece, right? So I'm going to put a little extra reinforcing in, right? Because it's very custom. As you bake it, you can vary those details to this particular process, right? So it's very customizable, where the last one was almost not customizable. Right? So there's advantages. Okay? The third is kind of a hybrid between the two, and it's called the slip form process, right? And so it's the idea is that we're taking the best of both worlds and trying to put them together, right? So we have a moving hopper, something like this, right? That we dump the concrete into the top, right? And it pushes the concrete down, kind of like the extrusion method where we get to the die, okay? The difference being that there's a certain length of form that happens, right? Instead of just pushing it through a simple die and getting the shape, right? We have some length of form that as we move, that form slips along with us, right? So, and I have some examples so that you can see it a little bit later, right? The tubes that form the slab cores move along with the hopper, right? So those little formworks that provide the shape, right, move along and then are slowly pulled out of the slab, right, as we continue casting the next piece of the slab. Okay? This gives us some flexibility to actually be able to put weld plates and that kind of thing in place, right? Because there's some customizability allowed. So in this particular example, this is close up of that photograph. We have the reinforcing under here, right? We're working down on top of that. The hopper, right, is producing is pushing the concrete into those formwork. The slip forms, right, are along in here. They get moved along as this process goes on.
Steel bin, and it has doors that open and close. This is the bottom, this is the middle, and over here is the top. And the top would leak into here, actually. The machine has like about 1,000 moving parts on it. These are the extruders, and the extruders are on 2 carriages like. So the outside carrier is every other extruder. As it's moving up, the middle carrier extruders are going backwards. So most of the compaction you get between the cores is due to friction of the oscillating cores line. So as these things here are moving, it's actually packing the concrete between them. The first layer of concrete will go to the bottom of the core, and if you look at the planks, it's about 1.5 to 2 inches depending on the plank size. Next layer of material would go to the top of the core, a little bit above. Last layer is only about a half inch or so above it. This will lay out 1 inch or so. These here tubes will actually drip water directly on top of the strand. Because it's such a dry mix, you do not get bondage like on the strand. So it will help make a slurry so it can bond better. The next layer, as it's putting it out, it has tappers like. Let me see if you can see any of the tappers tapping, and over here it's dripping. So it's hard to visualize, but this thing is on here and it's going this way. These topping, we put in broom thinness, a thick, smooth, depending on the topping of it.
How often does a machine like this break down?
I don't know.
Depends on the day. Yeah, good day or bad day.
There's an awful lot of moving parts. It's a high maintenance machine. It has about 100 zip pins that you have to move up constantly.
We can move on. Okay, so the next logical question, right, about this stuff is I have these elements. How do I tie them together? Right? How do I make this a uniform piece? Okay, 3 common connections: bolting, welding, and grouting. Right? And this is primarily for column to column, column to beam. Right? We already talked about the topping compound joining slabs together. Right? So grouting, right, is basically saying that an exposed metal connections, right, are dry packed with grout. Okay? That's not to say that the grout is dry. Right? It just means that it has very little water in it, so it's really, really stiff. Right? But it's called dry packing. Okay? So the idea here is that we have a metal connection and we're covering it up with this grout. Right? We're packing that in around that metal connection. Okay? So if we look specifically at a column to base connection, right, something like this, we have our reinforcing that's already in our base, which would be cast into the foundation, right? We have these pieces that extend up, right? Our dowels, so to speak, right? Then we have our precast element that has a nice steel plate on the bottom that's going to allow us to lower it down over those, right, anchor bolts, right? Once we get that into place, it looks something like this. The nice thing about this is we have the ability to add shims, right, add a few extra washers on one side and get that perfectly plumb, right? Because the bolts, when they're cast in the concrete, as much as we try to make them absolutely perfect, they're usually not, right? And so this gives us some flexibility to adjust for our overall plumb, right, in this particular case. After we've done that and we've bolted it into place, then we're going to put that grout to cover up as much of the metal connection as we can, right? Protects it from weather, protects it from rust and that sort of thing, right? Another example here along the midsection of a column, right? So if we had a building that spans more than one floor, right, and we were using these precast elements, if we're going to tie column to column, right, same kind of thing happens. We have our upper column coming down over our lower column. We have these cavities that are intentionally left vacant so that we can attach our bolts together and bolt these two pieces together. After that happens, we can go ahead and grout and fill in. Right? So if we're doing a column to a beam, right, we need some way of tying those pieces together. And so we can do that using post-tensioning, right, or we can do that using weld plates, which I'll show you in the next slide. So in this particular example, right, it's a post-tension tendon. So the idea here, right, is we have a cavity on each side, on each beam, right? Then we thread a rod through the beam, or cable, depending on what you're doing, through the column itself, right, out the other side into this pocket, right? And then we can tighten it or pull it from both ends, tie those two pieces together. After we've tightened it, right, we can grout over this little pocket that's left, right? And now suddenly our piece is one uniform connection, right? So that's one way of doing it, right? The other way of doing it would be to do a column to beam connection using a weld plate, right? And so the idea here, right, we have that little ledger that's sticking out, or corbel. We have all our reinforcing. We have a weld plate that's tied into the steel of the beam itself, right? When that comes over here, there's a weld plate that's been embedded in the column, right? And we weld this joint together. So we now have steel that's attached to the steel inside this column, steel that's attached to the steel inside the beam, and the two sets of steel are welded together, right? After this is done, we'll pour a topping layer that covers up this welded connection and also covers up the tops of the beams. Yes, sir? Yes. So that weld plate isn't just arbitrarily stuck into the concrete. It's tied into the reinforcing of the beam itself, right? So we're actually tying the reinforcing to the reinforcing, not the concrete to the concrete. Okay? Which should make some sense because what we're trying to tie together is tensile forces, right? The concrete, by compression, if one is resting against the other, it's going to handle compression stress just fine. It's when we're trying to pull them away. So really the ideal thing is to tie the steel, which is resisting the tension or the tensile forces in one piece, to the steel that's resisting the tensile forces in the other piece, tie those two together, and that's what performs the structural joint for us, right? So here it is there, welded to the steel cage, right? Here it is here, welded to the steel cage, and now the two get welded together. Okay? If we extend this even further, right, we put our hollow core slabs in the same situation, right? We have steel that's running along in between these two slabs, right? We also have this gap on top of the beam, which we saw earlier in the photographs, that has the little loops that are embedded in the beams, right? All of this gets topped together, or in this particular case, they're just putting grout in between and they're leaving this as an untopped hollow core slab, right? I would feel better if it was a topped hollow core slab, right? But depending on the engineer, they're going to specify different things, right? So here we have topping on a double T slab, right? We have our two T's put together, right? We put reinforcing on top of that, and we put our topping right on top of that to tie the whole piece together. Make sense? Yeah? Okay, so hollow core slab with a topping layer, right? Notice these are those cavities that I was talking about before, right? Those always exist to help tie the two slabs together. Sometimes they have the network of rebar that ties it together, depending on their scale. Sometimes it's just a keyway, right? And then we have the reinforcing running across the top, and then the 2 inches of topping layer on top of that. Okay, so we'll do a few examples, right? And this first example is exactly what you want to see because you can't really tell that it's a precast concrete building, right? And the point of showing something like this is that you really don't know from the outside that a building is precast. Certainly there are buildings like Fry's, right? Now that you know about the double T systems, right? You go to Fry's and you'll say, oh yeah, this looks like a precast building, right? But there are other buildings that are made up of precast elements inside, columns, beams, slabs, right, that look exactly the same as a building that's built in a different manner from the outside. Okay? So it doesn't mean they have to look like a prefabricated building. But there are certainly some big advantages, right, to the world of precast fabrication, right? And so this is a very good example. This is a university in Japan, and it was a very tight time frame from when they got the commission to do this building, right, to when they had to have the whole campus built. I think it was a year and a half. Okay, and so when they got the starting commission, they said, "Great, we're going to build this building. It's all going to be site cast concrete." Okay, and they started working through the design process, and things took a little longer than they wanted, and they got stuck in approval processes and whatever. And in that process, they lost about half the time of construction. Right? And so they had to open the university, they had to get the buildings done, and they didn't have enough time to do it. Right? So they switched methods, and they said, you know what? We're going to use as much prefabricated concrete elements as we can. Right? There'll still be a little bit of site cast, but we'll switch to the prefabricated elements because all of those can be made in bulk off-site, and it dramatically decreases the time for us to build it on-site. Right? We only have that half, 3/4 of a year left, 9 months left to build this. If you can prefabricate all these elements, we don't have to wait for our concrete to cure before we can move on, right? So it can go up much, much faster, which is what ended up happening here, right? And so these are a variety of examples that show you, kind of what the university looks like. So each of these is a precast element. That's a column that's been precast, right? If we look here, there's a beam that's been precast, right? The stairs were precast. All these pieces came together, right, from off-site. Right? If we look here, right, another good example, right? This shows us formwork, so we know that was site cast, right? There's our little formwork pattern. But if we look at all these elements, right, those are precast beams. These are precast columns, right, that are put together, right? That's a steel truss, not concrete, but we'll talk about trusses in a bit, right, when we get to steel. If we come over to this half of the building, look at the repetition, right, of all these elements. So this whole facade, it's a really long, slender building, right? We're reusing these elements. They were able to cast all those ahead of time, bring them to the site, and assemble the building very, very, very quickly. Yes, sir? Potentially, right, in certain places. This is cut halfway into the ground, so I'm suspecting that a lot of their site cast concrete had to do with retaining walls and those kinds of earth loads in terms of prep for this particular site. There are always going to be some pieces that are cast on site that tie these pieces together for seismic reasons. So depending, the best example around here, which I don't have pictures of because you can go there yourself, right? Worcester Hall in Berkeley, the architecture building, which everybody thinks is ugly, that is entirely made of precast elements like this would be. It's almost right on top of the Hayward Fault, so we have those same issues of how do we tie the building together. So the building itself is put together in this same kind of manner. Precast wall elements, right? Precast floors that have topping on them that kind of tie the whole system together, right? The problem with Berkeley's building was in its foundation, which is why it got the very poor rating when it came to the seismic zone. Like they've been doing all these retrofits along the way. So in about 2000 to 2002, the building underwent a $20 million retrofit, right? Which a lot of people are saying, well, wait a minute, like why didn't you just build a new building instead of spending $20 million on this building? And the answer was it would have cost $40 million for the new building, and it only cost $20 million to fix it. So they basically what they did is they took the building and they added cast in place. Right, this is where I'm getting to your question, right? They said, here's our precast building. It's not particularly stable, so what do we do about it? And so they took the front of the building and they took the back of the building in this tower, right, part of the building, and they said, we're going to pour, right, in place site cast tubes, right, on the back half of the building, 2 tubes, and on the front half of the building, 2 tubes, right? And those 2 tubes in the front and the back are providing our primary structural, like, lateral loading strength, right? And what they were able to do is they divided up those tubes on each floor and made them classrooms, right? So on the back half of each studio floor, there's 2 little classrooms, right? And those are the primary lateral loading support for the tower, right? They also went underneath and completely dug out the existing foundation, got rid of it, and poured a new raft-style foundation, which is giant. And I forget off the top of my head what the spec was on how many cubic yards of concrete, but it's just an absurd amount of concrete under the building that provided an entirely new foundation for it. So they tied these tubes into that new foundation. Now the building's seismically stable, right? So a lot of times on something like this, you can build the bulk of the building using precast elements with just a few site cast pieces that'll then provide all the seismic stability for your particular building. Great question. Okay, another example from the outside, all those precast columns, again, repeating themselves. From this side, right, we see the same thing, right? Each of these can be a precast element, right? This column can be precast. These wall panels can each be precast, right? The stairs and stuff were stuck on the outsides of this building, so they were easy to prefabricate in steel, right? So you kind of get the theme of this was designed to go up as quickly as possible. Okay, so that's it for tonight, right? You guys get off early. You get a half a class. If you have any comments or you want to talk anything specific about how you're pouring your particular beams, right, I'll be here for the next hour and a half to talk about it. And if you don't, enjoy a slightly less of a class today. Remember, there's 2 chapters for next week, Chapter 8 and Chapter 9. So you have a little extra time. You could do the reading ahead, right? Or not. You guys have a good night.